Hello, and welcome to Materials Unlocked, the podcast where we take a look at the lesser-known subject of material science and try to unlock its mysteries. My name is Dr. Lewis Owen, and I'm a lecturer at the University of Sheffield. In each episode, with the help of some students, friends and colleagues, we're going to delve into a particular topic and hopefully unlock its potential. This week, we're going to be talking about advanced manufacturing. So, as always, I'm joined on this voyage of discovery by some of our current students, and this week it is my great pleasure to introduce Ben, Jolly and Jacob. Ben, Jacob, I wondered if you could both just tell us a bit about what you study and things. So, Ben, we should perhaps tell the listeners that you are one of my PhD students, supervised by me. Could you tell us a bit about what you do, what year you're in and things?
Of course. So I'm a third-year PhD researcher, and my current research is on reconstructing the structure of multi-component alloy systems. So that's alloy systems of three or more, generally speaking, atomic species, using total scattering. So that's X-ray and neutron scattering analysis. We take all of those X-rays and neutrons and we bounce them off our alloy, and we take all of that radiation, reconstruct it and say, there's where all the atoms in the system are.
So basically the idea is we're trying to understand the material structure and how that affects its properties using these advanced scattering techniques.
Yeah, I would say that's a good summary.
I was going to say, it's always funny when PhD students explain their topic in front of me as their supervisor, because they have this slightly panicked look on their face of sort of, oh my God, am I saying the right thing here? How did you come into material science?
So I'm a physicist at heart. I would still call myself a physicist. Controversial.
That's all right. I'm a chemist at heart. Always will be, but there we are.
But material science seemed to be a good way of applying my physics knowledge. That was the way I saw it. And there was a master's available in material science, and I thought, well, this would be a good avenue to pursue. And solid state physics in particular is the avenue that I kind of pursued there, metallurgy in particular. But ultimately, I finished my master's, and I kind of still had a craving for more. So here I am doing a PhD, and luckily my PhD kind of followed on from my physics background, and I'm still working in solid state physics.
But it was really only, were you aware of material science when you were at school, or was it only once you got to university and were sort of already doing physics that you then sort of became aware of it? Who was the first person who said to you, do you know what, a material science master's might be in your future?
Truthfully, no one ever told me about material science at all. Honestly, at school, I had no idea about material science whatsoever. I thought it was kind of just the broad chemistry, biology, and physics, and maybe engineering if you wanted to go a step further. But to me, material science wasn't really on the radar until I was doing my physics undergraduate, and there was a module on material science and physics, and particularly I think it was semiconductors and things like that. But that was my own research led to that. No one really forced me in that direction. To be honest with you, I think it would have been nice earlier on in my career to know that there was more of a conglomeration of ideas in other sciences.
At school, material science is often folded into physics if it does appear at all in the syllabus.
Yeah.
Often that's where it comes sort of into the structure and things like that. Jacob, how about you?
So I'm a third year PhD researcher as well. So my work is slightly more lowbrow and more big picture. What I deal with is sustainability of railway infrastructure in particular. So that's all about understanding how the products are made, how they're used, and eventually what happens to them after their functional life is over, and trying to improve that picture. I think you're covering that at some other point in time.
We've got an episode later in the series where we'll be talking about the sort of the big picture and sustainability, recycling, and things like that, and thinking about life cycle analysis. But yeah, it's obviously an incredibly important thing in materials at the moment, particularly with the goals that are being set.
Yep.
Absolutely,
absolutely pivotal in obviously mine's rail and transport, and without understanding how your materials and what your materials do during their life and afterwards, it's impossible to reach any kind of net zero.
And how did you come to sort of material science and
so I am a mechanical engineer. I have a master's in mechanical engineering from Sheffield. I was actually more interested in just doing a PhD and getting that higher qualification. So I was looking around and I wanted to do something in rail because that's what I'm interested in, and saw this opening in the Advanced Metallic CDT.
So a CDT is a Centre of Doctoral Training. Yeah. So this is one of the mechanisms that we use to train PhD students at the universities. So.
And so they're designed to kind of, there's lots in different subject areas, and they're designed to try and get people to move into those subject areas. The subject of the particular PhD interests me. I enjoy working with my current supervisor. And so, yeah, it was just a kind of natural step, and I'm now a materials scientist.
So was your supervisor someone you'd worked with previously?
Yes, yeah.
Because I know sometimes people sort of carry on from master's projects and things like that.
So that's how I knew them, yeah. So, yeah, none of us are material scientists by the sounds of it.
Yeah. So today, then, we're going to be thinking and talking a bit about advanced manufacture. So do either of you sort of have any experience with advanced manufacture at all? Have you got any sort of understanding or background or...
I can't say I have a background in it. As a physicist, we tend to keep ourselves to our numbers and our code. But no, I mean, I've brushed upon it. I can't say I've ever been particularly invested in that side of things, but it's something I've been interested in over the years.
How about you, Jacob?
Beyond my mechanical engineering training and seeing some of the machines here in Sheffield and other places, no, not particularly.
So in the mechanical engineering degree that you did, is there much talked about the manufacturing process of particular materials and things like that, or is it mainly focused on, once we've made the object, using it and things like that?
Mainly the latter, but there's definitely an increasing head towards understanding how those materials are made. That obviously influences how they can then be used.
Well, that brings us very nicely to me introducing our specialist for today. And it's my very great pleasure to introduce Dr. Felicity Freeman, who's a lecturer in the Department of Mechanical Engineering. Felicity, welcome to the podcast.
Hello, thank you for inviting me.
Yeah, it's our great pleasure, and it's fantastic to have you here. So I wondered if you could just begin by telling us a little bit about your research and what you do, and possibly your background in material science, because as you say, you're actually in mechanical engineering now, but your background, you've been in material science prior to that and things. So.
Yes, it appears that I am the only metallurgist in the room. I currently am a lecturer in the mechanical engineering department. I am specifically within the manufacturing engineering group there, and my background is partly material science and partly manufacturing. So I arrived at Sheffield about 8 years ago to do my PhD. That PhD was looking at additive manufacturing, so what people may have heard referred to as 3D printing, and specifically using that for stainless steel. But prior to that, I worked in conventional manufacturing. So I spent 12 years at Rolls-Royce working on manufacturing components for gas turbine engines. So the kind of engines that you would see on your plane for going on holiday. So I've seen manufacturing from a big production scale, churning out thousands of parts a year, through to the very small scale stuff that we now do here, trying to make one part and hope you make it right. There's some very different challenges with those two things, but there's also a lot of similarities in terms of understanding how to control your process, understanding where your variation may come in, even things like if you've tried to make some parts and they've come out wrong, realizing that is a learning opportunity, and sometimes they go wrong because the machine felt like it on that particular day. But also sometimes they go wrong because you just didn't understand the science well enough, and working out how to use that to your advantage and go, okay, well, that one didn't work, but I know why, and that one didn't work, and I can now do this to make it better, and all of that kind of iterative process of trying something and learning from it. And every time you make it wrong, you've gained something by it, even though it might not feel it.
And I think that's something really sort of valuable to remember about scientific research in general. And it was something that we talked about on a previous episode with Dr. Kathy Christophou, where she mentioned sort of happy accidents and things, and, where those things sort of, you do something accidentally and then it leads to a new discovery of a new material or something. But actually, when things go wrong, there's that learning opportunity of understanding of sort of, why did this go wrong? As you say, was it just a freak blip on the machine that particular day? Or is there some fundamental reason why we can't do things in that particular way? And then how can we build that into our process of manufacturing or experimentation going forward and things?
Yeah, I think it's a really interesting one, sort of understanding where the boundaries lie for developing a new process, developing a new material, developing a new way of doing something, that we come up with good ideas, we try them out, and then sometimes we come across a barrier. And even just the fact that that barrier exists, or that all of a sudden the process doesn't work when you try and do it in a particular way, that's really useful knowledge. And it's something that I think gets left behind a lot of the time, that people don't write that stuff down because nobody likes to record their failures. But very often the failures are what you need so that people don't repeat those mistakes again in the future.
Yeah, you sometimes hear people talking about, we should have journals of negative results.
Oh, it'd be so useful.
And sometimes you see these, occasionally you'll see a paper or something where there's a one sentence line that says, the investigators tried to make this to no avail or something like that. And you think within that sentence is sort of 9 months of testing, lots of different things and trial and error and mistakes being made. And that knowledge sometimes, as you say, unfortunately gets lost. And we probably need to get better in science in general at sort of making sure that those negative results are recorded and kept somewhere so that, they're... And actually, very often they do appear in PhD theses. I'm looking at the PhD students in the room. People often have whole chapters sort of saying, these things didn't work and things. And I learned all of these things from it. And hopefully that guides us to the next process going forward. One of the things that you sort of mentioned there was additive manufacturing and 3D printing. And this is something I wanted to sort of, bring up and sort of explore a bit with you. Because I think 3D printing, if you go back, I don't know, but certainly when I was growing up, I won't say how long ago that was, I leave that to listeners' imaginations. But when I was growing up, 3D printing, no one sort of mentioned it or had thought about it at all, really. And then sort of at some point, maybe while I was at university and things, suddenly people started to about 3D printing, and you'd see people start having these little models that were always, models of, a cartoon character or something, or like, that was made in plastic or something that someone had printed and things. And these things sort of started appearing in people's sort of vision. People started to become aware of them and things. But actually, beyond just sort of making a fun little object, like it's potentially incredibly useful and powerful as a technique for manufacture.
Yeah. So as a technique for processing plastics, it's probably been around between 20 and 30 years, depending on where you look. And that's gone from quite blue sky conceptual stuff through to I can now go down to a shop or go online and buy a desktop 3D printer that I can set up at home and print some funky shapes.
Yeah, I was going to add, I'm sure some listeners will have 3D printers at home, I'm sure.
Yeah, and there's open source software to support that. So it's become very accessible as a technique for hobbyists and for people who want to make widgets at home to fix certain things around the house or whatever. Sort of that big story arc has happened on polymers, on plastics. There's stuff that's ongoing on the research side on plastics, lots of stuff to do with how it can be more widely used in healthcare and also for sort of structural applications. But where my research sits is sort of running in parallel with that, but looking at its application for metals. That's followed a similar trajectory in terms of its research, but sort of lagging behind by about 10 years. And the reason for this is driven by the fact that it's just a lot harder to process metals. It's harder from the perspective of health and safety. It takes a lot more energy to melt a metal than it does to melt a plastic. So we've got there's many, many different processes out there for additive manufacturing or 3D printing of metals. And one of the things, if people start looking online, that you'll notice is there's a lot of different terminology. Mm-hmm. But broadly, a lot of that terminology aspect is individual companies coming up with their own brand name for their machine.
But a lot of the underlying techniques are sort of the same or similar.
It looks widely more complicated than it is.
Yeah. Before we delve into some of the more specific details about, particular metals, types of processes and things, I wondered if you could just briefly sort of tell us, sort of why additive manufacturing? I mean, why is this potentially more useful, better than, the conventional ways of doing things?
First thing I would say is it isn't always. As a headline, it's often a lot more expensive to make something by additive than to make something conventionally. And by conventional processing, I mean things like casting, so pouring liquid metal into a mould and letting it solidify. Forging, which is to take something that's already solidified and is approximately the right shape and then hammering it out into the finished part. Machining, so just cutting off the excess and getting down to your finished shape. So these techniques, these conventional processing techniques, have been around, in the case of casting, for about 3,500 years. They're pretty tried and tested. We know them, we understand them. 3D printing is really, really good if you've got something that's a fiddly shape, a very detailed shape, where you can't go in and machine it afterwards. So if we think about something like a honeycomb or lattice structure, that's often what people have been looking at using additive for. So something which is what I would term re-entrant, where you've got features that are inside the component that you can't get at after it's been made.
Okay.
So if you want to build, a part for a jet engine where you want to have holes that you can put inspection into afterwards. So quite a complicated route through a component, a hole that runs through it that you can poke a thermocouple or something down afterwards, where if you made it as a solid, the route that you'd want to poke the thermocouple down is too convoluted to be able to machine it out. Whereas if you build it by 3D printing, you can build that route in as part of the manufacturing process. Lattices, as I say, lightweighting structures.
Lattice structures are these sort of repeating structures that's going out in sort of multiple times. So like a honeycomb where you've got that sort of big structure that you're building out, but therefore you've got sort of holes in the material in some of these sort of lattice structures. Is that right?
Yes.
Mean that you can potentially have something that's a bit lighter weight because you've got less material?
Yeah, so a honeycomb is a really nice example. You can imagine that if you were trying to cast that, so if you're trying to make something where you poured metal in and you'd end up with a honeycomb, you'd actually have great difficulty getting all the pieces of your mould out at the end. Whereas if you can build it up by layers, you've got a lot more flexibility about that structure, and you can play around with how you want the holes in your honeycomb to sit relative to each other, and things like that. So 3D printing is really good where you want flexibility over the geometry you're building. It's also very good if you've got something. So I think this has been used for a jet engine application where conventional manufacture required a particular component, I think it's a fuel nozzle, to be made in 3 separate pieces, because to try and make it as a single piece all in one go was too complicated. And because you've made it in 3 separate pieces, you have to then join those pieces together. So you've got to build in features that allow you to join them together, and that adds weight. Now, the problem is for aerospace or transport applications like your rail applications, anything where you're adding weight, that weight has to be carried. So that means more fuel, and that reduces your efficiency of your overall process. So with additive, if you can join things together in a way that means you're only manufacturing one piece without all of those joining features, you reduce the weight of the overall component and you save some fuel.
And I suppose also the joining features will potentially have slightly different properties, and so could then be sources of weakness or something where the material might fail, whereas having something that is that sort of continuous material, not always, but in some cases, having something that's then that continuous material might mean that it's got not only the weight advantage, but better properties, removing those chains and things.
Yeah. If you're looking at joining 2 pieces together and you've got to, say, put a bolt through something or a screw through something, you've then got to make a hole. That hole is a stress raiser. That's potentially going to be a source of failure. If you can design that out by using 3D printing to build it all in one go, and make it nice and continuous, you get the best way of improving a component is to eliminate your sources of failure. So that's where its strengths really lie. But it is a business case trade-off. It is more expensive very often. So it's a case of understanding.
Is that more expensive even by removing an additional step in the manufacturing process? It's still more expensive to make it.
Not necessarily. That's where the trade-off lies. Okay. So if you're machining it, how much does your tooling cost? If you can reduce your material usage by printing it, then that's a benefit. If you're machining, then you're cutting material off and it goes on the factory floor and it goes in the bin. So yeah, all of these things are a trade-off. I think very often people come in saying, 3D printing must be better. It's better in the right circumstance. So we wouldn't want necessarily to go out and print actual rail.
Yep.
Actual rail is probably always going to be cheaper to make conventionally. But what we might want to do is use 3D printing to repair existing rail. Because if we can use it as a repair technology, then from a sustainability perspective, it's going to be better to repair something than make a new one.
Yep.
So there's always a bit of a trade-off here, and that's where a holistic view of manufacturing capability is really more beneficial.
And I think it's one of the things that we face in material science in general. We talked about this a bit in a previous episode, is often we have to make that balance of properties and think about, if I have a particular property and I make that better, it might make some other property worse. And we have to prioritize and decide what we're going for. Here, the cost is a literal cost of money versus the benefits that might come from having, better shape or something like that, or fewer points of weakness, and then, balancing those different things.
Can I just ask, we've gone from talking about cartoon characters on desks to talking about, aerospace here. We're talking about jet engines. How big or how small can we go with these machines?
It very much depends on how big a machine you want to buy. There has been a bridge that's been printed,
like a physical whole bridge, or a...
I think it's a pedestrian bridge. I think it's in Amsterdam. It's very much a question of what the terminology I tend to use is what platform you're looking at. So what 3D printing process. There's a number of processes out there. So some processes are good at fine features, but can potentially only build things up to sort of Coke can size. Some processes can build things the size of a car, but you don't get quite the same resolution, quite the same level of detail that you would. So it's a case of choosing the right process for the application that you're looking at. So if you want to build a bridge, you build it using something that is designed for building components of that scale.
I've seen videos not on additive manufacture of metals, but people doing 3D printing with concrete and things like that.
Oh, yeah.
Building, houses and sort of modular structures and things. In my mind, when I picture a 3D printer and the sort of things that you see in people's houses, it's in a sort of little square frame and looks like a sort of little cube, and you have this thing that sort of tracks around and builds and things. But these are big sort of mechanical arms moving around and, gigantic frames and things to build these meter-sized structures and things that's being made. Let's talk then about some of the more specifics with metal manufacturing and things. So you said that there are, I think you referred to different sort of platforms for different sort of machines and things like that. There are different types of metal additive manufacturing. Is that right?
Yes. And there's a number of different ways you could look at this. So one question is what's commonly referred to as what's the feedstock? So what type of material am I putting into my process? And this generally falls into two categories. The one that I primarily deal with is metal powders, but there are also systems that will take a metal wire. The wire feed methods, that's where your sort of bridge building world lies.
That's more similar to the kind of modern plastic 3D.
Yes, that's much more sort of closely aligned to the desktop plastic printing. The metal powder platforms are very much well into the high-tech industry scale. So this is where aerospace, automotive, and when I say aerospace, that's not just sort of the jet engine world. That's also people looking at building components for satellites and all sorts of stuff like that. So it's high value, high technology, generally low production volumes. So that's where that world lies. And then there's a second part to this, which is how am I heating this up? So I think people are comfortable with the idea that if I start off with a metal, be it a powder or a wire, and I want to form it into a different shape, I'm going to have to melt it. And I can melt it using a laser, which is the most common approach, or I can melt it using an electron beam. The reason the laser is the most common approach is that the electron beam is quite limited in that you can't use it with a material that's magnetic. It reacts badly.
Yeah.
We'll park electron beam and go on to laser. The laser is what we use the majority of the time. And here at Sheffield, we've got 2 different laser approaches. Both work with lasers, both work with metal powders, but their setup is very different. So one process we've got is called directed energy deposition. And again, you'll find this referred to under a wide variety of different terms. That's the term that I use for it. This is basically a hot glue gun. So what we have is a laser beam coming down from the top of the machine, and the laser beam comes out through a little copper cone. And the little copper cone has got a channel in it, and we blow powder, metal powder, out through the channel into the laser beam. What that means is that we've got this stream of metal powder, and we've got this laser beam that's at about 300 or 400 watts of power, and they come together, and if we've set it up correctly, they come together in the same focus on the surface of our component where we want to deposit the material. So the powder lands, and the laser melts it and melts into the base plate or whatever we've put on the machine bed. The laser melts that powder and incorporates it into this substrate. We can then move the substrate around, and we can move the laser around. And so we've got complete flexibility about where these two go in relation to each other. And that means that we can build up components like, for example, like a vase. So something that's got some curvature to it, so we can tilt and move around, and we've got a lot of flexibility about where we go with that. But when I say it's like a hot glue gun, if you imagine taking a hot glue gun, you start squirting the hot glue out in a circle on a piece of paper, and then you gradually work up, and you just keep building on top of the layer you've already got. You can go up as a cylinder, or you could kind of work out very gently and make a bit of a cone, and then come back in and make a bit of a vase shape with it. So that's one of the processes we've got.
Are there issues? Do you get issues with melting the stuff you've already put down?
You need to melt into it a little bit so that you actually stick your layers together. So the track we're depositing is normally of about, let's say, 1 millimetre in cross section. You want to melt back into the previous layer by about 1/5 of that.
Right, okay.
So that you get good adhesion. The other process we run here is one called laser powder bed fusion. That sounds quite technical. It's also called selective laser melting. That's a slightly historical term for it. And this works in a very different way. So this works by spreading a layer of powder out, and then you draw on it with your laser wherever you want it to be solid. And when you draw on it with the laser, you're melting the powder layer that you've put down, but again, you're melting into the layer below as well. So that, where you've drawn, melts and sticks to what's underneath it. And then you put a new layer of powder on, and you repeat the process. What this means is that over time, you build up, again, layer by layer. All of these processes are layer by layer. You build up your geometry, but it can cope with much finer features generally. But the constraint is that you can only build vertically. So if you have overhanging features, which we do with jet engine parts or satellite parts, whatever, if you have overhanging features, you need to support them. And for people who've used a polymer desktop printer, they'll have experienced this issue as well. That the open source software you use with those very often puts those support structures in. And so when we think about, 3D printing gives you full flexibility, actually there's more to it than that, because if you're looking at something where you've needed a support structure, after you've built it, you need to get rid of that support structure. So you still have a machining step. It's just a different machining step. Mm-hmm. There's a lot of processes out there, and they've all got slight differences and slight tweaks, but that's sort of generally where the processes sit.
And sorry, can you use any metal for these things? Is this, are we working on every single alloy in the world can be 3D printed, or are we?
Well, the majority of what we do concentrates on steel alloys, so iron-based, nickel alloys, which is a lot of the stuff that we do for aerospace, and titanium alloys. So that's kind of 80 to 90% of what we do. You can use these processes for ceramics. We'll park that as a concept for the moment. Might come back to it later. One of the difficulties you've got is actually back in the physics world, which is that we use lasers with a wavelength of 1070 nanometers. You're relying on the alloy that you're using absorbing that wavelength of laser energy.
Right, okay.
One of the alloys we've looked at in the past, copper, does not absorb particularly well at that wavelength. So you either have to use slightly strange processing parameters to get it to behave, or use a different wavelength. So going out and buying a different laser and plugging that in, and then setting the process up again with a different laser.
And your face tells me that's not common.
And if you're only going to use your machine for processing copper, it's worth it. If you want to be able to swap between doing copper on Monday and steel on Tuesday,
right,
then it's a little bit fiddly.
So then picking up sort of there, talking about the processing, and you talked earlier about sort of developing the process, and here you've given us an example saying if we're switching between metals, we'll have to, change that process, change the laser that we're using and things. But even within, if I were just sticking with, let's say I'm sticking with steel for the moment, and I'm doing that, I would imagine there's quite a lot of development to be done just thinking about, how quickly you move it. If we go back to your glue gun analogy and things like that, if I move my glue gun very slowly, I end up with great sort of globs of glue going along, whereas if I move it very quickly, I end up with the sort of strands and things. So I'd imagine there's quite a lot of understanding that needs to go into the speeds, the laser powers, all of those sorts of things.
Yes, absolutely. And it kind of hits us in two aspects. So the first aspect, picking up your question earlier about the remelting, if we don't remelt into the previous layer well enough, so if we go too fast or we don't turn the power up high enough, then we won't remelt into the previous layer well enough. What that means is that when we've got to the end of our build and we look back at it, maybe cut it open, we see a load of holes because we haven't put enough heat in to create a dense component. That causes us a problem because every single one of those holes causes our structural integrity to be degraded in some way. So if we then use that component in something where we're loading it, particularly maybe a cyclic load, all of those little holes act as stress raisers and act as initiation points for failure. Similarly, if we put too much heat in, we could actually boil the material. And when we're talking about complex alloys, which have got 10, 12 different elements in there, all of which have a critical role, if we put so much heat in that we start to boil metal, which does happen, then we start to lose some of those elements. So what we've actually built at the end doesn't have the composition of the powder we started with. So we might have built something that's dense, but unfortunately it's the wrong thing. So porosity and temperature control are really critical from that perspective. But the other perspective, and this is where sort of we get back into the material science rather than manufacturing, is around the microstructure. So one of the critical things for the performance of any engineering material is the microstructure. So it's what's going on inside our lump of metal. When we cool something very quickly, we get a very different microstructure from when we cool something slowly. And if we look at a complex geometry, so let's say we were going to try, not even a complex geometry, we were going to try and build a mug. So we start off at the bottom of the mug and we're building, each of our layers is a complete circle. We might build complete circle layers for about 1 centimetre of depth. We're building a chunky mug. But all of those layers, we're depositing material for a long time. That could be a minute and a half of deposition. We're putting a lot of heat in because the laser's on for all of that time. And because we're putting a lot of heat in, the whole thing starts to warm up quite a lot. It's holding heat, and that means that as we're depositing and as that our little melt pool is solidifying, it's solidifying quite slowly. So we might get quite a coarse microstructure. Then we start to move up into the sort of sides of the mug, and all of a sudden we're zooming round the outside. We're absolutely flying. What does that mean in terms of our temperature profile, in terms of how the whole mug is behaving as we're building it, is that suddenly it's starting to cool down a lot faster. We might be using the same speed and the same power, but we're not spending as much time on each layer. And because of that, we're cooling down faster and we end up with a finer microstructure. And in terms of the metallurgy, in terms of the mechanical properties, those two things are very different. So we've built with what on paper looked like the same parameters, but we've ended up with something that has very different properties. This becomes potentially problematic if we look at building a complex component where we need uniform properties. And it then drives us into the question of going down a modelling route of predicting what that temperature profile looks like, and then trying to adjust the build parameters, adjust our power and adjust our speed so that we end up with uniform properties that we can predict and we can understand.
So as you say, we've got these differences in cooling regimes, and when we've got this much slower cooling, the growth of the crystals inside, they can grow much larger and you end up with this coarser microstructure. But as you're saying, this sort of prevents, I suppose, any sort of standard recipes for sort of processing, because with different shapes, you end up with this different cooling regime just because you've got a different thickness. Sort of flipping that on its head, though, you've given an example where you're saying you then may need to account for this to create a uniform structure. But could you, in fact, therefore do it the other way and sort of build specific areas within your material that have certain properties and things? Because in a previous episode, we've talked about how what we're trying to do in material science is understand particular structure property relationships and develop the structure to give us a property. So could we then actually use this and flip this the other way to allow us to build a particular material with a particular property?
So this is exactly what I'm trying to do at the moment.
Fantastic.
Some particular types of steel undergo a phase transformation. So this is a rearrangement of the atoms inside the material. And they go through this either because of how they've cooled down or because of deformation. One of the interesting things with this particular behaviour in steel is that it's a transformation of something which is weak and ductile, so something that yields quite early but is quite flexible and can be deformed for a long period of time and a large amount of deformation. It transforms from that kind of behaviour to something which is strong and brittle.
So strong but likely to shatter very easily.
Yeah,
as opposed to something that soft and bendy.
Yeah. One of the things we're researching at the moment is using this to create what's termed metamaterials. A metamaterial is something which has different functional properties throughout its structure.
So this is using the same underlying material and then affecting the properties by changing the structure of it at a certain length scale, or is it combining different materials as well, or possibly both?
It could be both.
Okay.
So a very simple type of metamaterial would be something like carbon fibre. So a carbon fibre board has got the fibres in it and it's got the matrix. So you've got two components there that are working together to give you properties that the individual components couldn't give you on their own. But really what we're looking at with metamaterials is taking that to another level and saying, can we modify the properties through the components? So not just having a composite which has uniform properties, but having graded properties. So if we looked at some kind of joining component or an arm on something, you might want a particular amount of load-bearing capability in one area, but you might want more ductility in a different area because it's experiencing different mechanical loading.
So you're thinking these materials would be for a specific or designed for a specific application?
Yeah, so bringing the material properties in as an additional design parameter that you can change through the material.
Yep.
So with the steels that we're looking at the moment, one of the things we've discovered is that depending on the build parameters that you use, so depending on the laser power and the travel speed that you use, that determines how much heat you put in, that determines how it cools down and solidifies, and that determines then which phase you get at room temperature. So we've actually been able to build structures where we can distribute this weak ductile phase and this strong brittle phase in different regions and get different mechanical performance out of the component as a whole. So if you just had the weak ductile material, it yields quite early, but it can cope with a lot of deformation. If you just have the strong brittle one, it can take a lot of load before it yields, but once it yields, it's absolutely useless. It's in little crumbly pieces on the desk. If you combine those two in different proportions and different arrangements, then you can get composite behaviour, which can then be tuned to the requirements of an individual process.
So you have this very fine tuning of properties for your particular component.
And that's, I think, one of the things when you asked the question at the beginning, what's the point of 3D printing? What's the point of additive? It started off, yes, I can make some funky shapes. But being able to do this kind of thing and really tune your material properties at a local scale, and I'm talking less than a millimetre resolution, that kind of scale, that's something that conventional manufacturing can't even touch.
You could have a different blade every time you made one, basically, right? If you were down a production line, you could have one has this properties, one has this properties. Yeah,
you can absolutely get to a point where you can tune your mechanical performance or even other properties. So we've also looked at it from magnetic perspective. So for electrical machines, being able to put magnetic and non-magnetic materials next to each other. And there are other routes to doing this, but they all use combinations of different alloys, a magnetic material and a non-magnetic material next to each other. The difficulty with all of those is when you come to end of life, you can't recycle it. It's like the sandwich packet that's a bit of plastic and a bit of cardboard. Yep. And it requires somebody disassembling it before you can recycle it. So you end up degrading the material value if you've put in lots of different types of materials. Whereas the advantage of doing it this way, of controlling your material properties within the build, but keeping the composition uniform, is you get to end of life and it's still the same material you started with. So you can put it straight back into your revert stream, you can remelt it, and you're back to where you started from. You have it's like glass. Glass you can just keep going round.
Yeah.
And how confident can we be in all of this? Because it's very primordial. It's it's a laser and it's crumbly bits of metal, and then suddenly we're launching it into space. How confident can we be when we say we can have these properties change? That's exactly what we're going to get out.
At the moment, we're doing a lot of testing. So this is a lot of what we do is very early stage. Somebody's had a bright idea, and we'll go and prod it and see if it works.
For lots of money.
What we're trying to do at the moment is build up our experience of doing this and making sure it's repeatable. So a lot of what I do is statistics-based, making lots and lots of something that should all be the same, and then going and testing them and looking at the population of results that I get back and deciding whether the spread of that data is acceptable.
So it's a tolerance. It's not a...
Yeah. And
Is repetition a challenge? Because obviously I think traditional manufacturing has got quite good at repetition.
yes, at the moment, repetition within a research environment on something like this is a bit of a challenge.
Okay.
But there are production uses of additives. So it's not something that can't be overcome with the correct process controls. But it's a case of, it's what I mentioned at the beginning with conventional manufacturing. A lot of it is understanding your process variables and controlling them appropriately. So all of these questions around process control can be overcome, but it's part of that maturity curve, the learning curve associated with any new manufacturing process. So just using 3D printing for metals, yes, we can make it repeatably. Using 3D printing to make metamaterials that have got different phases in different places, we're getting there. And then it's a question of bringing in people doing modelling so that we can be sure we understand the processes that are going on and that are driving all of this technology. The other part to it really is finding out where the boundaries are. So it's great if I can make something again and again and again, but if I never make it wrong, I don't know where my process fails. So what I actually need to do is have a go at making it wrong.
And that's where the science comes in.
That's where the science comes in. Yeah.
Do you think the research and the interest into this is being accelerated because of its potential advantages over... So obviously these traditional manufacturing techniques have been around for a long time, some of them, and have been improved over that, whereas additive seems to have accelerated very quickly in a short space of time.
Yes. I think we see it because additive is new within our lifetime.
Okay.
I think all of these technologies have been through that. It's just that we've not seen it.
Yeah, okay.
There's a curve for when something's new and everybody loves it, and then people get disillusioned and it
Comes back.
yeah. And I think we're going through that with additive, that people have gone, oh, additive exists. Oh, look, I can make cartoon shapes. I think when I was trained on the machines, we made minions.
Yeah.
A lot of the stuff you used to see at conferences a few years ago were, oh, look, we've made a funky shape.
Yeah. So it's actually gone past the novelty stage, you think?
Yeah. That doing fancy shapes is lovely, but it's not science.
Yeah.
You don't get kudos points for it. It's now a question of what can additive give us that conventional manufacturing can't. I think also just a question of bringing additive in instead of seeing it as something apart from conventional manufacturing, just seeing it as a technique that sits alongside. Because as I mentioned earlier, if you're going to build something that's got supports, as part of your manufacturing process, on a holistic sense, you need to make sure that those supports can be machined off successfully. If you don't think about that when you're designing your 3D printed part, all of a sudden you've made it and you can't get rid of the supports. Well, that's no use to anybody. So it's a case of looking at a complete manufacturing supply chain and saying, how is this going to behave at every stage of that process? And additive is just one of those techniques that sits alongside everything else.
Obviously, at the moment, one of the big drivers in a lot of fields, and particularly material science, is thinking about sustainability and things. And you referenced the recyclability of the material. And if you have multiple materials going in, then it possibly makes it difficult for recycling and things. I wondered, and also thinking about Jacob's comment about doing repeats and things like that, and the reproducibility and having to do it lots of times and things. I wonder what the sort of the greenness of this as a procedure is in terms of energy usage, and is that one of the things is that the reason it's so expensive, and is that one of the balances that we have to make of, yes, it might be less energy efficient, but actually it gives us a part that's going to behave better, and so over the lifetime of the material, that's a good balance to pay in order to sort of balance the books, if you see what I mean.
Yeah, and it's a really interesting question. So very often people approach it saying, oh, well, 3D printing is a really efficient process because any powder that doesn't go into my part, I can collect and reuse. Yes, you can. One of the things we have to be careful of with that is as we're processing it, very often the powder picks up oxygen. If the oxygen level gets too high, then it will degrade the material properties. So yes, we can recycle powder, but we need to look at controlling or at least monitoring the oxygen level and understanding the impact that's going to have on our finished component. A bigger aspect, though, is how we get our metal powder in the first place.
I was going to ask about this. Yes.
Yeah. So if we take two processes, so we take 3D printing and we take casting, and we're going to cast and print the same component. So let's say it's a turbine blade. Both of them are going to use the same alloy. So for both of them, our first step is we need to manufacture that alloy. So manufacturing that alloy, going out and getting a bit of nickel and a bit of aluminium and a bit of this, that and the other, putting them all together and casting a billet of our feedstock, that's neutral between the two processes. If we're going to do conventional casting process for a turbine blade, we then just take that billet, melt it and pour it into the mould. We'll have made it oversize, so we need to machine some of that off. So we produce some waste as part of that. But that waste can generally go back in to be remelted next time we need some new alloy. For 3D printing, we take that same billet and we melt it, but now what we need to do is put a lot of argon in. And argon is reasonably abundant, but it requires its own manufacturing process to get to it. And the reason we need that argon is that the majority of the powders we use are gas atomized. So what this means is we've melted our alloy and we pour it into a flowing stream of argon. And we use argon because it doesn't react with the alloy. So we're not changing our composition. We're not putting in weird oxides or anything like that. And the argon literally blows this stream of molten metal apart, and we end up with a fine powder. But the amount of argon we use is massive. When we're looking at life cycle analysis, we need to take into account how much argon we're going to be using, and therefore the manufacturing requirements for that argon, be it in terms of energy, be it in terms of the carbon associated with that manufacturing process, and that needs to be factored in. And that's something which I think people are picking up on more now as part of the overall cost of a 3D printing process. But it's something that I think was maybe lost in the noise a little bit previously.
You were talking about one of the things that was really cool with your metamaterials was thinking about tuning this property on the sort of I think you said the sort of millimeter scale and things like that. I wondered if you could just briefly talk about the fineness of feature that you can actually control. Because one of the things that we said was this sort of the benefits of additive manufacturing was to create these shapes. You might have a channel that you can put an instrument like a thermocouple, which is a temperature sensor, in and things like that. What is the sort of fineness of that feature, and are there certain factors that affect the fineness of the feature we can control and things?
Yeah, so the main constraint is the size of melt pool. So the size of molten region that we create when we're doing the build. And that's really driven by how big a laser you're using. So this isn't necessarily how powerful it is, it's how big a spot size you're producing. So our powder bed systems, which are the ones that are good for sort of high resolution, but up to sort of the size of a Coke can or a bit bigger, they use a laser which is 70 microns across. So what's that? Less than 1/10 of a millimeter. If we're looking at creating a metamaterial, we probably don't want to be relying on a single track of a different property to the adjacent one. We're probably looking at having 3 or 4 tracks adjacent as a minimum.
So if there's a problem or a failure with one, it's still enough.
And that you get enough of each type of material to start seeing different behaviours as opposed to all it sort of smushing together. So that's kind of why I've said about a millimetre for the resolution of that. The other process that I mentioned, the directed energy deposition one, where we blow powder into the laser beam, that laser is just slightly smaller than a millimetre across. So that we're looking at creating a much bigger melt pool. We've got that slightly coarser resolution for the size of feature that we can look at. But that machine can build things up to 60, 80 centimetres in size. So that's where our scalability comes in, really. The finer features you can build on smaller components. The bigger components, you're restricted to having slightly coarser features.
Yeah.
If you go up to building a bridge, which we can't do on our machine here, but it is possible. If you go up to building a bridge, you're probably looking at something which has got a resolution of around maybe 2 to 3 millimetres.
Brilliant. Well, thank you, Felicity. That's been really fascinating, and that's so interesting to find out more about this technique, which, and as I say, most people, I think, have become familiar with from a sort of plastics point of view, but I don't think they necessarily appreciate the fineness with which you can control things and the way you can give these fantastic properties and select various properties for various areas and things, and you know the sort of fine control that gives us. Just before we finish, is there anything else that you'd like to share with the listeners?
The only thing I would say is something that I actually used to say a lot to people I was working with in my previous role, which is that from my perspective, engineering research is all about looking for patterns. It doesn't really matter what process you're looking at. It's taking some data and looking at it and saying, where are the anomalies? Where's it not worked? Where's it worked? Or even just looking at a group of data points and saying, what are the similarities between all of these? What are the differences? If you can start by finding patterns, then you've got something to go and investigate. That's all I do. I look for patterns.
I work looking at patterns as well in a slightly different sense, but in the sense of crystal structures, which we'll talk about more next time. But I'm all about patterns, and I completely agree with you in that. Ben and Jacob, is there anything else that you'd like to ask Felicity, or any final comments that either of you have?
I suppose, but my major question is really, this is something that it's emerging. It's an emerging technology, and it's something that people are starting to adopt. But, you know, nuclear fusion is always 30 years away, or whatever the statistic is. You know, how close are we to adopting additive manufacture more broadly across the spectrum for the things that we talk about in the lab, or, you know, when we're building a standard component? Is this something that's already very prevalent, or is this something that's due to take off, or are we really kind of at the plateau?
For polymers, it's there. For metals, it's always going to be an expensive technique, I think, compared to making a widget using conventional machining. But for the components where it buys its way in, it's production ready. So, yeah, aerospace parts, some automotive parts, dental implants, things like that, where it can buy its way in because it can achieve geometric flexibility that conventional can't achieve, then it's production ready and it's in use.
Cool. So is it purely cost, do you think, or is there people don't quite understand it, or they don't trust it, or is there another reason?
Is there going to come a point in time where people have a metal 3D printer at home?
That's really what I want. That's
I think the health and safety implications around metal powders and lasers are probably going to make that unlikely.
Yeah.
Could a random machine shop somewhere have one? We're maybe 5 to 10 years from that. As the process becomes easier to optimize, then I think that will get there.
I guess that's really my question, because obviously all of these traditional processes are expensive still, but they're able to do things at a large scale and therefore get that per unit cost down. I guess that was the question, is do you think additive will ever reach that? Yes,
I think it's always going to have some health and safety implications that most conventional manufacturing processes don't have. But I think it will get there.
Felicity, thank you very much for joining us today on the podcast. And thank you, Ben, and thank you, Jacob, for joining us as well. And thank you, listeners, for joining us on this episode talking about advanced manufacturing. Hopefully you've learned something, and hopefully you'll join us next time when we're going to be talking about characterization. Thanks very much for listening. If you want to join the conversation, you can find us on Instagram at Materials Unlocked. If you want to find out more about the topics that we've covered and the work that we do, a link can be found to our website in the show notes. Our thanks to the Advanced Metallic Systems CDT, the Henry Royce Institute, and the Department of Material Science at the University of Sheffield. See you next time.